Hi, welcome back to C23 Classroom channel. Today, I would like to discuss with you about boundary layers, and we focus on turbulent boundary layers. As in our previous slide, we already discussed that there are two types of boundary layers. One is laminar boundary layers and the other one is turbulent boundary layers. So if we see this diagram, we could say that for the first time when the uniform free flow hit the surface here, the slip condition, no slip condition will occur and it will create velocity profile. At the same time, it will create boundary layers. However, at this region, the velocity profile will flow in certain ways, and the velocity is quite laminar. It is called, this region is laminar boundary layers. However, after a certain distance, the direction of velocity here is become rough and unlawful. So it's called the transition. After that, when all the velocity here will flow in turbulent and so on and so forth, so the boundary layers here were called a turbulent boundary layers. However, in real application, the transition of boundary layers from laminar to turbulent is very small, so it is not our major concern in this subject. So for this syllabus, so we have three conditions. One is laminar boundary layer, which means that it is fully laminar boundary layer. Means that if we have a plate here, all the boundary layers here is in laminar flow. And then now we are discuss about turbulent boundary layers. Please bear in mind that we assume that all boundary layers here was in turbulent flow. So mean it is fully turbulent boundary layers as shown here. And then at last we will see about the condition of laminar and turbulent boundary layers like this. So the situation is when we have a thin flat plate like this, and we found that laminar boundary layers is quite dominant in the flow, and then it continues with the turbulent boundary layers before it ends at this edge. For laminar boundary layers, please bear in mind the velocity profiles are listed as shown here. So it starts with the power of 1, 2, 3, and 4, and sinusoidal profile. So as I repeat again here, our basic assumption is all region in laminar is laminar boundary layer. Okay, so we go for turbulent boundary layers. For turbulent boundary layer flow, we have two methods for obtaining the information desired. So method one is power law form, and it is easier, but it is a little bit less accurate compared to the method number two. So method number two is called the empirical form. It is more complicated, however, the result is more accurate compared to the power law form. In our syllabus, we are focusing on power law form because it is quite easy, and students could derive by himself on paper in final exam. Okay, I hope you could imagine about turbulent boundary layers. Okay, let's say we have one flat plate like this, and we have a free stream velocity here flow from left to right. When it hits the plate here, so no slip condition occur, and it creates resistance, and it creates boundary layers. However, the velocity here is chaotic, and it creates a turbulent flow inside the boundary layers, and we assume that the boundary layers can be drawn a little bit rough like this. So bear in mind that in this calculation, we assume that all the boundary layer here is in turbulent flow. Let's say we have a thin flat plate like this, and we have free stream velocity flow from left to the right, and it creates boundary layer like this. So we assume that the length of this thin flat plate is L. So to calculate the Reynolds number for this condition is we could use the Reynolds number equation rho u x over mu. So we could replace the x here as its length, and sometimes it can be written as rho u l and mu, where the rho is the density of the moving fluid, u is the free stream velocity, x is the length of the flat plate, and mu is the dynamic viscosity of the fluid. So please bear in mind that in boundary layer, it is very crucial to differentiate between small u and capital U, because capital U here is the velocity of the free stream velocity, and small u is the velocity of the local velocity profile here. So we will discuss about turbulent boundary layer by using power law form. So in this method, we feed the data from the velocity profile with a power law equation. The power law form can be simplified as this one. So please remember that turbulent boundary layer velocity profile u over u is y over delta by the power of 1 over n. And n here, the value of n is depend on each Reynolds number. So we could simplify it as is as this. So if n is equal to 7, it is okay for us to say that the Reynolds number is between 5 times 10 by the power of 5 until 10 by the power of 7, and 8 for this range, and 9 is for this range. And normally for common turbulent boundary layers, it is okay for us to take the representative value of turbulent boundary layer as n equal to 7. So sometime in another textbook, they will write that turbulent boundary layer is 1/7 power law, means the velocity profile here is y over delta by the power of 1 over 7. So another thing that you need to understand in that turbulent boundary layer, we will solve this problem similarly with von Karman equation. So means first we need to do the von Karman equation to get the shear stress, and then we need to get another value of shear stress by using Newton's law of viscosity. However, for turbulent boundary layer, we cannot use the Newton law of viscosity, because in Newton's law of viscosity, we have du over dy at y equal to 0. So this term will give us 0 in value. So for example, we have u over u equal y over delta by the power of 1 over 7. So if we do the du dy, we get this term, and when we substitute the value of y equal to 0, we will find that du dy is equal to 0. In terms of mathematical solution, it is correct. So there are no mistakes in this calculation. But for solving boundary layer in turbulent flow, so we say that the value 0 here is not matched with the real situation. So means that we cannot use Newton's law of viscosity in calculation of turbulent boundary layer. So what we need to do? So we need to get an empirical relation that introduced by Blasius formula. So we will get this Blasius formula by do the empirical calculation. However, in our syllabus, the value of shear stress from Blasius calculation will be given in the question. Okay, let's say we have a problem like this. So we have velocity profile of 1/7 power law, which is y over delta by the power of 1 over 7. and we say that we could get the shear stress from the Blasius calculation is 0.0226 rho u square mu over rho u delta by the power of 1 over 4. Bear in mind, sometimes in another textbook, they will use nu over u delta. So you need to understand the relationship between dynamic viscosity, mu here, with kinematic viscosity, which is nu. So let's say we want to define what is the boundary layer thickness delta is. So we start with the von Karman here. So von Karman is tau equal rho u square d theta dx. As we know, we need to find what is the value of theta for 1/7 power law. So we calculate the value of delta by using this equation. We substitute the value of u over u with the previous value, which is y over delta by the power of 1 over 7. In this equation, we found that theta is equal to 7 over 72 delta. So we substitute in this equation the value of delta, and then we could simplify the calculation into this term. So we could say that this is equation number 1. So again, I would like to mention here that we cannot use Newton's law of viscosity because the value is 0. So what we use is we use the shear stress from the Blasius calculation. It will given in the question. So let's say in this question, the Blasius shear stress value is 0.0226 rho u square mu rho u delta by the power of 1 over 4. So what we need to do is we equating both value of shear stress. So this is the shear stress from the von Karman equation, and this is the shear stress from the Blasius empirical calculation. So what we need to do is we need to grouping the delta here means that we bring the value of delta by the power 1 over 4 here and remain with this d delta, and then we bring all the another terms to the right hand side, and as we did previously, we integrate both sides and we take assumption as x equal to 0, we'll create delta equal to 0, and it will give us constancy equal to 0. Then we could have this value after the integral process. So later on, we need to simplify this term. So we need to come with the delta itself. So we could simplify it as delta is equal to 0.3721x over Reynolds number by the power of 1 over 6. So this is also, when we substitute the value, we will give the same final answer with this equation. However, so it is compulsory for students to know how to convert this calculation into Reynolds number here, because in common equation they will transform this equation to become Reynolds number terms here. So the idea is simple. So to have Reynolds number here, we must have rho u x over mu. However, we have one element of x at the top section. So what we need to do is we just multiply with x over x by the power of 1 over 7, 1 over 5. So now we have rho u x, and then we multiply x by the power of 4 over 5 with 1 over 5. So we get x by the power of 1. So that's why we have one term of x at the top here. And then we could continue our calculation to find what is delta star. So this is the velocity profile. So this is the equation for the displacement thickness. Then we get it is 1 over 8 delta. We replace the value of delta, and then we get the value of delta star as this one. So this is the momentum thickness. So we have delta. Again, we solve the equation. We get the final answer here. We substitute the value of delta here. with the previous answer, and we could say that theta is equal to 0.036x over Reynolds number by the power of 1 over 5. So this is the shear stress. So this is the shear stress from the blast. So I would like to remind you again here. So we have two terms of shear stress. One is from von Karman equation, and another one is from the Blasius empirical calculation. So I advise you to use this one because this equation is fully developed. For von Karman equation, we still have d theta over dx, which is the equation is not ready to use yet. You need to do the integral process to get the final answer. So it is better for you to use the value of shear stress here from the Blasius empirical calculation. Substitute the value of delta could lead us to get this answer as our shear stress term. And then to calculate our drag force here, so this is the common equation for drag force, the summation of shear stress and area. So B times dx will represent the area. So we integrate from 0 to L, which is L is the length of the flat plate. So we substitute the value of tau from this term from our previous calculation, and we could get that drag force as this one. And then to calculate the drag coefficient, as we know that CD is equal drag force over 1 over 2 rho U square B and L. B is the width of the plate and L is the length of the plate. We substitute the value of FD, and finally we could say that CD is equal 0.0722 over Reynolds number by the power of 1 over 6.